Hi, I was asked this question. It's a really good question. 8.3, number 3, from Math 127. So it says, suppose that a circus performer is shot from a cannon at a rate of 80 miles per hour at an angle of 60 degrees from the horizontal. The cannon sits on a platform 10 feet above the ground. Construct a set of parametric equations describing the performer's stunt. And that right there is, I'd say, 90% of the problem. Then sketch a graph of his flight. How high is the acrobat 1.5 seconds after leaving the cannon? How far from the cannon should the landing net be placed if it is to be placed at ground level? At what time will the performer land in the net? If I got blurry there with my camera, 12-foot high wall of flames is placed 70 feet from the cannon, will he clear it unharmed, is what it says there. Okay, so let's find out. So we're doing 3A. So for the first one, we have two components to consider. We have x equals some function f of t and y equals some function g of t. So that the horizontal position is based on time and the vertical position is based on time. I'm not really keen on the way the picture is shown. I like to do it's just probably a linear way of thinking that here he is, cannon, going to fire off like that. And we know that this initial angle is 60 degrees. But he has a vertical component. He'll go up, then come back down again. So the y equals g of t describes going up and coming back down. That's a parabola. And then x equals f of t is just the horizontal component. Now, our x equals, what we have is an initial velocity, but it's not going to be going the entire velocity. We want to break this initial velocity into a vertical part and a horizontal part. The horizontal part could be found by using cosine function, and the vertical part would be sine function. So our initial velocity is 80 miles an hour. And the platform starts off 10 feet above the ground, so he does have an initial height of 10 feet. Okay, so I don't know why it keeps doing that there. So x will equal to what? Let's see. 80 miles an hour is the initial speed. That's if he's going there, but the horizontal part of that would be times cosine of 60 degrees. So probably should convert this to feet per second because we have feet in here as well. So that's 80 miles per hour. So let me just erase that first. 80 miles per hour times 5,280 feet per mile times 1 hour over 3,600 seconds. So this is our initial velocity. That's going to be what? Where did I put my handy dandy calculator? Here it is. I get 117.33 feet per second. Okay, so the initial velocity in feet per second is 117.33. So for the x, for the position function, x is 117.33 times cosine of 60 times t, I should have there. because that gives us a velocity. This is the x part of the velocity times t gives us the position, so how far across here it would be. Okay, what is that going to give us? X equals what? And my calculator is in radian mode, so of course I think we all know, clear, that cosine of 60 is 0.5, right? So this is 58.67t. Okay, so that's our x function. X of t is 58.67t. Now y is a little more work to do. So y is this going to be our basically the equation we use for something falling, and it's a negative 1/2 a t squared plus v naught t plus h naught. So in this case, it's our a is acceleration due to gravity, and that's going to be negative 30 or 32 feet per second. So negative here is because it's falling. So y of t is negative 1/2 times 32 times t squared plus, now our v naught, so if we look at the initial velocity for the vertical part, that's going to be our 117.33 times sine of 60 degrees times t, and our initial height is 10 feet. So our y function is going to be, well, negative 1/2 of 32 is negative 16t squared plus, and I'll do the 117.33 times sine of 60, and that's going to give us 101.61 t plus the 10. So we have our two functions in our horizontal component and our vertical component. And then once it's to sketch a graph of this, and we could put this in our calculators under the parametric, or we can plot points. In fact, it might be easier to plot points if I put this in there under the parametric part. And I can go over to the other, the table mode. So I'm going to do 58.67t, and then I'll do negative 16t squared plus 101.61 t plus 10. Okay. Let's see. Those are in there. Go over to table.
Where's Jim?
Let's see. So we'll start at 0. Let me set this table up to do auto. We'll start at 0 and go by ones. Okay. So at t being, time being, we'll go 0, 1, 2, 3. We have x of t, and we have y of t. So we have 0 at 0. Then we're at 58.67, and we're at 95.61. Then we're at 117.34, then 149.22, so we're definitely still climbing vertically, and then 176.01, 170.83, and 234.68, 160.44. So we're kind of slowing down and going up. See that bigger increases, and the increases are getting smaller. Then we're at 293.35, then 118.05. So now we're heading down. 352.02, 43.66, definitely going down. And then 410.69 and negative 62.73. So definitely come down. So we can stop there. And if we were to graph that, and let's see. Let's start up here. 160 was our high, so we went a little above that. So let's call this 160, and maybe we'll go down by 40s. 120. I feel like we should go 120 here, then 80, 40, and hey, perfect. That worked out well. Horizontally, we went out to 410. So let's go out to 400 by, I'll go by 80s. 80, 160, 240, 320, 400. So let me go back to my calculator because I have everything in here. So we start off here at 10 feet. So it wasn't 0, 0, it was 0, 10. Now we have at 58.67, we're at 95.61, so roughly speaking, 95, right about there. And then at 117, say it's here, we're at 149. Then we are, let's see, hang on a second. I'm looking at my data again. I think okay, I didn't catch that it was going down. This was the peak and it started going down there. Okay. And let's see, where are we now? So we're at 176, so right about here, let's say, up to 170. That may not be the highest we got, but it's up there. And then we are at 234, and we're at 160 now. And then we are at 293 and 118. 352, we're at 43. And then finally at 410 we're below the ground. So this is in essence the path that was taken by the, roughly speaking. Okay, so there's the path. Now, part C says, how high is the acrobat at 1.5 seconds after leaving the cannon? Okay, that's not so bad to calculate. The height for t equals 1.5, y equals negative 16 times 1.5 squared, plus 101.61 times 1.5 plus 10. And that should be I get 126.415, so 126.42 feet. That's the height at that point. Now, by the way, if this did start at 0 and we want to know the ground, I mean, the middle would be the highest point, but we don't know. That's not the case here, so we can't do that. And then it asks for D, how far from the cannon should a landing net be placed if he is to be if it's to be placed at the ground level. So basically we want to know when the y, at what time the y is going to be 0, and then we can put that time into the x to get the horizontal distance out. So we're going to first find t for y equals 0. So we'll set that negative 16t squared plus 101.6t plus 10 equals 0. So we're going to solve for t. Our a is negative 16, our b is 101.6, and our c equals 10. So if you recall the quadratic formula, I usually say x, but I better make myself say t equals negative b, so it's negative 101.6 plus or minus the square root of b squared, which is 101.6 squared, minus 4 times our a is negative 16, and our c is 10, all over 2 times a is negative 16. Get the part under the radical. 101.6 squared minus 4 times negative 16 times 10. I'll do this. That's okay. That's negative 101.6 plus or minus the square root of 10962.56 all over negative 32, which is negative 101.6 plus or minus 104.7 all over negative 32. So it's negative 101.6. I should, yeah, I'll do the plus 104.7 over negative 32, and negative 101.6 minus 104.7 over negative 32. So in the first case, we have negative 101.6 plus 104.7. Divide that by negative 32, and we get negative 0.96875. And that's what it would have been if we could go back here. That's like going back in time. We can't do that. In the other case, it's negative 101.6. I left off a decimal, but whatever. We're good though. Minus 104.7. And divide that by negative 32. And I get 6.44 6, so I'll say 6.45 seconds. Now for part, finish this off, x of 6.45, so 6.45, the horizontal distance would be 58.67 times 6.45, which is 378.42 feet. That's where the net should be placed. Okay, now part E. At what time will the performer land in the net? From part D, time would be 6.45 seconds. We just did that. Boom. And then for part F, it says, if a 12-foot high wall of flames is placed at 70 feet from the cannon, will he clear it unharmed? So x equals 70 feet. At what time would that occur? So that would be 58.67 t equals 70. So T would be 70 over 58.67, which would be 1.193 seconds. So let's see what his height would be at that time. So y of 1.193 seconds is going to be negative 16 times 1.193 squared plus 101.6 times 1.193 plus 10. I don't need the parentheses on the 10. And what will that give us? Negative 16 times 1.193 squared plus 101.61, that's what we originally had, times 1.193 plus 10, and I get 108.45 feet. So yes, he will clear the wall of flames. Hope that helps. I know that's a tough problem. I think one of the tougher problems in the entire section. So kind of funny that's number 3. Let me know if you have any questions about this. Thanks. Bye.